Right, hello Year 8. So what we're going to do today is we're going to do sort of a thought experiment, an exercise. And last lesson I asked you, do you think aliens exist in our galaxy? And discuss and explain your reasoning, but we never really got to the crux of the matter. So I'm going to give you a bit of information and then set you about a task about what you think might, if or not you think there are aliens in our galaxy. So give you a little bit of information to begin with. Um, there are an estimated 100 billion stars in our galaxy. So that's that number. So this is our galaxy, the Milky Way. This is what it looks like. And you are about here. So Earth's solar system, so our solar system with the sun, the Earth, and all the other planets, Mars, Jupiter, we are about there. And our sun is just one star of about 100 billion. Now, here's the thing, this is where the numbers start getting a bit crazy. There are an estimated 200 billion to 2 trillion galaxies in the universe. So imagine this is our galaxy with 100 billion stars. We think it might actually be more because the little red dwarf stars are quite hard to see. There could be 200 billion to 2 trillion in our universe. Okay, therefore the total number of solar systems. So, say for example, if each star had its own solar system with planets, that is the number of potential solar systems there are in the universe. That's 1 to the power of 23. Okay, now that is an enormous number when you consider there's only been there's only been 10 to the 16 seconds since the universe actually begun 13.7 billion years ago. So potentially a huge, huge number of stars out there, some of which will have planets, some of which won't, but obviously a lot of possibilities. Okay, so I suppose the fundamental question is, what do we need for there to be life? Now, what does the planet need for intelligent life? Well, since we're the only example of intelligent life we know of, let's use us as an example. So, firstly, a planet must be in what's known as the habitable zone. Sometimes it's referred to as the Goldilocks zone because it's not too hot, it's not too cold, it's just right, just like Goldilocks and the Three Bears. And you can see Earth is just in this habitable zone. So for example, take a planet like Mercury. It's too close to the sun. It's too hot. Planet like, say, Mars or Jupiter. Well, probably not Mars, actually, more like Jupiter. It's too cold. It's outside the habitable zone. But if the strength of the sun is just right, then you will be in this habitable zone. Now, if the star is smaller and colder, the habitable zone becomes closer to the sun. If it's a really big, bright star, the habitable zone moves outwards. So, say, for example, a planet orbiting out as far as Jupiter could be in a habitable zone if it's orbiting a big, bright star. Anyway, the whole point is it's got to be in just the right area so that you can get liquid water on its surface, because water, we know at the moment, is fundamental to all life. But that's not the only thing that you need for life. For example, okay, they think that Venus once had water on its surface, and Mars, for some reason, they lost that liquid water. So, other things you need. Your planet needs to have a solid surface. So planets like gas giants like Jupiter and Saturn are unlikely to have any kind of life that we'd certainly recognize on it because they've got no solid surface. You'd also need a core that gives off a magnetic field. So that would probably be an iron nickel core. Now, luckily, Earth has one of these, and all that swirling mass of iron and nickel creates a magnetic field that extends all the way out into space. This is why we can use compasses always pointing north. And as you can see, this magnetic field protects us from some of the hot sun's harmful radiation. Okay, now without this magnetic field, Earth's atmosphere would have been stripped away off into space billions of years ago. But as it is, this magnetic field deflects some of those harmful particles from the sun around the Earth and only lets just the warming light through. Another thing about Earth as a planet is it's big enough, it's got enough gravity to hold on to its atmosphere. So a combination of Earth's magnetic field and a combination of it being actually big enough to hold on to its atmosphere means an atmosphere has actually developed and stayed with us. For example, Mars did have an atmosphere that was like Earth once, but its magnetic field switched off and the atmosphere got stripped away over a few million years. Okay, a few other things that help us life. Now, a moon. Earth has got a moon. Now, this was a result of a very early collision in Earth's history. But what the moon did is it stabilized the spin of the Earth. What happened is the Earth would spin radically towards the poles and then towards the equator. So what would happen is we'd get really freezing cold winters. Like imagine the worst kind of Antarctic winter, like -80, and then during the summer you'd get stupidly hot, like 100-degree deserts. And some animals have adapted to some seasonal change, but these are two real extremes, and nothing could really survive these two sorts of extremes. So the moon is really important because it stabilizes the spin of the Earth, and so Earth only wobbles a little bit, giving us quite gentle seasons. Okay, and other things you might need is you need a planet which has got volcanoes. Reason for this: volcanoes expel gases that can form into simple organic chemicals, which in turn can form complex organic molecules and ultimately simple life like bacteria. If these start photosynthesizing, they'll make oxygen. Okay, so quick review. These are some of the things you need for life. You need the planet to be in just the right place for there to be liquid water. You need to have an atmosphere and to be able to hold on to that atmosphere. So you need probably to have a magnetic field, and you need to be big enough to hold on to its atmosphere. So there's enough gravity there. A moon is almost certainly what's needed to stabilize the spin, and so you don't get extremes of temperature. And then you need volcanoes spewing out gas, which can make this liquid. Oh, sorry, which can make give you the molecules you need for simple life. But then, of course, if you get simple life like bacteria on Earth, that's how it was for many, many years. Consider our tree of life. Okay, these are some of the complex organisms which exist today, and then some of the ones which have gone extinct. But this is the really hard part. Okay, simple life must have time to evolve into intelligent life. So let's just have a look. All of this variety of life, so all the things that we know about, from lions, bears, whales, elephants, butterflies, insects, even things that have gone extinct like dinosaurs, all of this evolved in the last 500 million years. Now, Earth is 4.5 billion years old. So, life probably evolved around quite soon after Earth was formed, maybe 3.5 billion years ago. But for most of Earth's history, there was no complex life, okay, let alone intelligent life. For most of Earth's history, we were stuck down here, simple bacteria or nothing. And then 500 million years ago, a random chance event happened. We think that what happened was one cell got inside another cell and created what we now know as cells that we're familiar with. And that meant that all this different life came into being. And that only happened once in maybe 3.5, 4 billion years. But then all of a sudden, life changed. We start getting these complex life. So it took 3 billion years just sitting there with bacteria in order for us to then get this intelligent life. Okay, but only complex life came along very recently in Earth's history. Okay, only the last sort of 15-20% of Earth's history has it been complex life. Okay, so the question is, could this have happened on other planets? Someone actually came up with a way of trying to work this out. So what I'm going to do is I'm going to post this link in the post for today's lesson, and we are going to use this, and I'm going to explain how it works. But firstly, I'm also going to post a couple of videos. One is about 4 minutes long, and the other is about 10 minutes long. I'd like to pause this video and then switch to the other two videos, and then you'll come back to this one in a few minutes. Okay? Okay, so welcome back. So you got a very brief introduction into something called the Drake's equation. Now, the problem with this is that it doesn't know what any of these numbers actually are. So n is the number of alien life civilizations that could be out there. Okay, but it doesn't know what R actually is. It doesn't know what FP is. It doesn't know what NE is. So what we're going to do is we're going to do a little experiment. We're going to try and play around with these numbers using this website here. And we're going to work out what the possibility of alien life is. So I'm going to go through this example with you. So once again, follow this in a moment. You're going to follow this link and you are going to work out what the odds are of there being intelligent life in our galaxy. So firstly, when you follow the link, you'll come to this page, okay? And what we can do is we can get a little bit more information. So first one was R. So we do R times FP times NE times FI. But luckily, you don't have to do any of that. The computer will do it for you. So the number of suitable stars, stars like our sun, that form in our galaxy every year. Okay, astronomers estimate that this number is about 1. Okay, so let's say one star forms every year in our galaxy. So we put that in. Then the fraction of these stars that have planets. 1 equals 100%, 0.25 equals 25%. So we put it in as a decimal. Okay, so let's say we're discovering these exoplanets all the time. Okay, so we thought planets were quite rare, but now actually think planets might be quite common around stars. So let's say 50%, so half of all stars have planets, so 0.5 in this case. The number of Earth-like planets, meaning planets that have liquid water within each planetary system. Well, at the moment in our solar system it's only Earth, but scientists have found evidence that both Venus and Mars and Earth at one time all had water on their surface and all at the same time. So let's say, gives you some information, but let's just say, for example, that maybe 2 planets have the right conditions just for liquid water. The fraction of Earth-like planets where life develops. Now this is tricky because water doesn't mean there will be life. But, for example, if you think all Earth-like planets produce life, your estimate would be 1. Okay, so we do it again as a decimal. If you think only 1 in 10 such planets produce life, your estimate would be 0.1. So let's just say life, maybe even just simple bacteria, is actually quite common. If you've got the right chemicals, you've got water, maybe it's quite common. So let's say 20% chance of that happening, so 0.2. Fraction of life sites where intelligent life develop. Now, for the purposes, we define intelligence as having symbolic language like maths or English or Japanese, since language is required for communication. If you think planets with life always produce intelligence sooner or later, your estimate would be 100%. If you think only 1%, it'd be 0.01. Now, this is difficult because it's a total guess. How inevitable, how likely were humans? Are we just a fluke of evolution, or is intelligence inevitable? So let's just say intelligence is quite a hard thing. Okay, I'm going to say there's only if you've got life, only a 10% chance of it ever evolving into intelligent life. Then the fraction of intelligent life where communication develops. So if you can become intelligent, you can communicate, will you? Personally, I think this is quite likely, so I'm going to go for a full-on 1. I think if you got the means, why wouldn't you? And then finally, lifetime of a civilization in years. So how long does a communicating civilization last? Humans, we've been communicating with telescopes for about 100 years. But how long does it last? A century, 1,000 years, a million? Your guess is as good as the experts. Now, humans have been building things for about, from mud huts, 10,000 years. So let's just say, on average, a civilization lasts for about 10,000 years. Let's put that number in there. 10,000. There it is. We then press calculate, and according to this, there would be 200 civilizations out there in our Milky Way galaxy right now. Okay, now here is your task. What I'd like you to do is clear this and start putting in some of your own numbers, and you can research what these numbers might be. For example, how many stars out there in our galaxy? Well, you can Google that and find out. Okay, how many stars have planets? Again, you can do a quick bit of research and put some of these numbers in, and you can play around with these numbers. But here's the thing, you're never going to get a definitive answer because we don't know what these numbers mean, but we can have a good go at guessing what they are. So your final task is this. Once you've had a bit of a play with the Drake equation, you can put your numbers in. I would like you to do this. So have a go at using the Drake equation, change the variables, see what kind of answers you get. Then take about half a page to a page in your book and lay out the arguments. If you think there are intelligent civilizations out there in space, and say why. Okay, so by the time you've had a bit of a go with the Drake's equation and maybe worked some of the, had a research some of the variables and then written it up, that will probably take you about half an hour or so to do that properly, probably a bit longer actually. Okay, then you simply upload your work. Now, do bear in mind there are a couple of links. There is the 2 YouTube videos that talk about exoplanets and Drake's equation, and then there is the link to the little calculator, this thing, the Drake equation calculator that I just showed you. All of those will be in assignments and also on the chat group. So I'll be online. If you have any problems, let me know. Good luck.